Hello everyone. In this video, I'm going to explain how to solve the two-sum problem. First, let's see what the question is asking us, or what is the problem to solve. So basically, we're given an array here, an array of integer, and by the way, I'm solving this in Kotlin. So we're given an array of integers, nums, and a target of type integer. And what we need to find is two number in this array, basically nums, that will add up to targets. We need to find these two numbers and return their indices. So basically, mainly that's the problem that we need to solve. Then we're going to look into the constraint and some examples here before we provide the solution. So we are given the fact that we have exactly one solution. So we know that there is exactly one solution, and we have the constraint that we should not use the same number, which is pretty obvious basically. We need to find two numbers that are distinct in that array that will add up to the target. Here, for example, there is an example. We have three examples here. So basically, let's look into them. We have nums, and the array has these numbers 2, 7, 11, 15, and the target is 9. And we have the output, which is 0 and 1. So basically, these are the indices. 0 is 2, and 1 is 7. And when we add these two numbers, we have 9. And here we have an explanation. Same for example 2. We have this array and this target, and the answer or the output is 1 and 2. So this is 1 and this is 2, because this is a 0 indexed array. So we have 2 and 4 equal to 6. Same here. And here we have the constraint. Basically, the array we have, like the array that's here, they name it nums. At minimum, it contains 2 elements, and at maximum, it contains 10 to the 4th. 10 to the 4 means 10,000. 10 to the power of 4. So this is the constraint on the number of elements we have in the array, nums. Then we have another constraint on the values of each element. So each element can be as small as minus 10 to the 9 or 10 to the 9. Same for the target. The smallest can be minus 10 to the 9. The biggest is 10 to the 9. 10 to the power of 9. And again, here we see that we have only one valid answer. Then we have also a follow-up here that basically they're asking us to provide, or whether we can come up with an algorithm that is less than O(n) squared time complexity, that basically is more time efficient than O(n) squared. First, I am going to provide a basic or intuitive solution that is O(n) squared, and then we are going to look into a more efficient solution. So here we're going to look into the primary solution, or a basic solution, if I can say, before looking into a more efficient one. So I'm saying basic because it's a solution that takes O(n) squared complexity. Basically, we're gonna loop for each element in the array, we're gonna loop over the array once. So it's gonna be n times n. We're gonna have an outer loop and an inner loop. And that's what I'm saying. This is kind of a brute force solution. So first I'm gonna write the outer loop of for. And here we're gonna use some kind of, I don't know, special syntax. Basically, I'm gonna use Kotlin syntax to be able to access the value and the index of the array. So first I'm gonna put index and here the value, and I'm gonna say in nums, which is the name of the array, but I'm gonna use this function with index. And since it's the function, we have to use the parentheses. And then we're going to go inside this loop. So here we're gonna use another loop. So this is the outer loop of the array. And then for each element in the array, we're gonna also loop again over the array to see whether we can find two numbers or two elements or two integers in that array that will add up to the target. Of course, with the restriction that we cannot add the same element with itself. That's the only restriction here. So I'm gonna say for j, which is the index. That's how it works basically. Using this notation, the first element here is the index and the second is the value. So j is the index and w is the value. So in nums with index, and here this is going to be our inner loop. And basically the condition here is, basically here what we want to do first is that we want to see if these two values that we have here will add up to the target integer. So does v plus w equal target? That's what we want to look for. But first, we want to also make sure that we are not having the same index. So because this outer loop is going to loop from 0 until the length of the array. And the same here is going to go from 0 to the length of the array. So here we could be in a case when we have 0 here and 0 here. We don't want to add, because the v and w are going to be the same number, and that's like the restriction here. Exactly. You may not use the same element twice. So to not do that, we are going to add a condition, an if statement. So if I not equal to j, only in that case we're going to check for this addition. We're going to check if this addition is equal to target. And if that's the case, it means that we found our answer. We have our indices. So we're gonna return int array of I and j. So basically we found our two indices, and outside the for loops, we also want to return something because we cannot leave this empty. Either we need to throw an exception here because it means we didn't find an answer, or we can simply just return an empty array. So return int array of. So let's test to see if this solution works. And yeah, so here we have the answers. Basically, that's for target 9, we have this output, and the expected is 0, 1. So we're passing the basic test cases. But as I said, this is not an efficient solution. This is an O(n) squared solution, and this would work as an answer. This will pass all the test cases. So basically, if we go ahead and submitted this would work, but it's not an efficient one. So accepted. And yeah. So we can look into the runtime. The runtime is pretty slow, 79 milliseconds, and the memory usage is 4816. So 79 milliseconds, it says it beats 5% of the solution, so it's a pretty slow solution. We want to look into a faster solution. And now we're going to look into how can we make this much more efficient. Now that we looked into a basic solution to this problem, we're going to look into an efficient one. Basically, one that will take less than O(n) squared to solve. So in order to do that, we're going to use a hash map, basically. And let's just declare one here. So val my map is equal to hash map. And this hash map is going to be of type int. Going to use a hash map here. What's a hash map? Basically, a hash map is a data structure that stores key value pairs. And looking up, like basically a lookup into this hash map takes most of the time constant time, meaning like O(1) time. And the idea is that for each element, we want to look up into this map and see if we have something, we have the complement. So remember, in the basic solution, we iterate through the array, and for each element, we iterate another time through the array to see whether we can find a complement. And this basically takes n time. So O(n) squared. Basically, n is the number of elements in the array. So the outer array, we're gonna go through it. Basically, the iteration is gonna take n time. We're gonna look into each element, and then for each element, we're gonna iterate through nums again to find a complement. So for each element, we're gonna have an O(n) time. The lookup is going to take O(n) time. With a hash map, that lookup can be turned into constant time or O(1) time. So we're gonna have O(n) times O(1), which gives us O(n) in the average case. I'm not gonna go into the details of implementing hash map here. We'll let Kotlin do that. But on average, it takes constant time lookup. And here, what are we storing in this hash map, basically? So we see that the type is integer and integer. And what we're storing is basically the index and its value. It's a little bit counterintuitive because here the key is going to be, the order was reversed. First, that's what I'm saying is kind of a little bit counterintuitive. We're going to store the value and its index. Here, the key, basically, we said the hash map is a key value, stores key value pairs. So the first int here is the key, and the second is the value. So, but here the key is going to be the value with the element in the array, and the value is going to be the index. So let's see how we're gonna do that. And this is going to be done in a for loop. And the solution is a little bit also counterintuitive, because what we're doing here is that we are looping through the array and we're looking up into this hash map at the same time that we're building it. So let's see how this is done. Basically, this is the outer loop. And in this case, that's the only loop we have. We don't have an inner loop. That's why this solution is an efficient solution. So for, let's say, index and element in nums with index, what you're going to do is that first we're gonna compute the complement. So we're gonna val complement is equal to target minus element. So basically, element is the element of the array we are looking at it now. So we have the target minus the element. That's gonna be the There's gonna be the complement. Complement. So that's gonna be the complement. And the complement, since it's a value, it's a key into this hash map. So we're going to see if our hash map has this complement. And that's what I'm saying. It's kind of, again, here, it's a little bit like counterintuitive, because the hash map at this stage is empty. But again, this is to be able to do this in one pass and make it more efficient. So bear with me a little, and it's gonna make sense. So first, again, here, what we're going to do is we're gonna check in the hash map whether we have the complement. So if complement, and here we're gonna use Kotlin syntax to check what we have in the hash map. So if complement in my map, basically the name we give to the hash map. So if complement in my map, it means that we found our answer. We have the complement. Now what we want to do is we want to retrieve the index of this complement, because what we want to return here are the indices. We already have the index of the element we're looking at now, and we want to find the index of the complement. So here we're going to have val complement index, and that's going to be my map complement. Because again, we said that a hash map is going to be the key value pair is going to be the value or the element and its index. The index here is the value. So val complement index, that's going to be the index of complement. And another thing that's kind of interesting to know is that complement index, basically Kotlin is going to return a nullable type, and that's another specificity with Kotlin is like nullability. So complement index is gonna be of type nullable, like, because if, for example, complement is not in the map, we're not gonna have any index for it stored. So we're gonna return my map is gonna return null. So to avoid an error or a null pointer exception, what we're going to do is to check whether complement index is not equal to null. And only then we're going to add it and return it to our array. So here if it's not null, what we do is return, and we're going to build our array here, int array of index, which basically is the index here of the element you're looking at, and the element here that we found. Complement index. So that's the case where we found our complement in my map. And the thing is that at this stage, when we are iterating, when it's our first iteration here, we know that we're not going to be founding the complement because the hash map is empty. We haven't built it yet. As we said earlier, we're building it at the same time that we're looking into it for this to be an efficient solution. So here we build it. I'm going to show you how we build the array basically, or the hash map, sorry. So we have my map, and we're going to put here the key, which is the element here. And here we're going to store its index. And basically that's how our map is built. And at the first iteration, this is going to be empty. So of course, we're not going to have a complement in the map. But as we go through the array, as we iterate through the array, this map is going to be built. And at some point, we're going to find the complement, basically. The complement, and through this basically subtraction, for each element, we know what the complement is. And at some point, the complement is going to be in the map. That's why I am saying it's kind of counterintuitive that we're looking first into it, into the map, before we have put anything in it. But first, this is not going to execute because the complement isn't going to be in the map. And here we're going to also, if we reach this point and we haven't returned anything, means we didn't find a complement, which here we're given, we said we're given that we have exactly one solution. So I don't think we're going to get, there is a case where we reach here, but still we have to have a return statement here. So it's going to be a return. And here we're going to return an empty array. So let's test this solution now and see if it works. So we have a complement error. Basically, it's because I forgot the parentheses here. And yeah, this is a function. So obviously we need the parentheses. What other errors do we have? Variable is unused. Let's see if it works this time. 21 where my map complement. It could be complement index. Sorry. So basically this is just a typo. Complement I just forgot the E here. So let's see if it's gonna work now. Return int array of. Again, this must be a complement. A typo complement. So basically it's saying that This is an unresolved reference because I basically mistyped it. Complement index. And basically here we see that this solves the problem. So here we have the solution. It passes the basic test. So let's see how it's doing with the overall test. And more importantly, let's look into the runtime. So we saw that the runtime was around 80 milliseconds in the past solution, and I think it was like better than 5% of the solution. Here we see that the runtime is 2 milliseconds. That's pretty efficient, and it beats 99.53% of the solution. So we know this is an efficient solution, and it's what we were asked basically. Can you come up with an algorithm that is less than O(n) squared time complexity? And that's basically the answer. And here we have basically the statistics. It takes a little bit maybe more in terms of memory, but that's not what they're asking for. They're asking for the runtime. Yep. So I hope that my explanation was clear enough. If you have any question, please leave them in the comment, and I'll do my best. I'll do my best to reply to it as soon as I can. Yeah, hope this was useful, and hope to see you in other videos. Don't forget to share, like, and subscribe, and see you in next videos.